Hi, Gregory Wrightstone here. Welcome to another episode of Climate Chronicles, episode 4. I'm really excited about tonight's show. We're going to be looking at a thing that's called Plate Climatology. It's actually pretty topical. If you're a climate geek or a geology geek, you're probably listening into this. And there was just articles this week on Antarctica. We'll talk a little bit about that. If you like what you see here and want to see more, go to my website, inconvenientfacts.xyz, to learn more about the commentaries, videos, interviews, and educational videos that we have. I want to introduce our presenter tonight. It's James Kamis, a retired professional geologist. He's got a BS in geology from Northern Illinois University and a master's in geology from Idaho State University. He's always been fascinated by the connection between geology and climate, and I love it because I'm a geologist. He's got 42 years of research and observation that's convinced him that geological forces have an underappreciated and underestimated effect on the Earth's climate and climate-related events, and he calls it the plate climatology theory. So I'm hereby dubbing him the father of plate climatology. Welcome, James.
Thank you, Greg.
And let me share my screen. We can get going here. And there we are. It's all yours.
Thank you. The plate climatology theory, how geological forces influence, alter, or control Earth's climate and climate-related events. So I'm not here today to convince you that the plate climatology theory is correct, nor am I here to convince you that the global warming climate change theory is incorrect. Rather, I'm going to present a plausible alternative explanation for many climate and climate-related events. Now, the idea for the plate climatology theory came to me in 1977 when, as a young graduate student, I observed two really significant events. The first one was the deep dive of the Alvin submarine off the coast of the Galapagos Islands. These islands are volcanically very active, and there's a big fault there that cuts a big piece of Earth in two. So the Alvin went down through the photic zone, which is where, at the time, most scientists figured was the majority of marine life. In fact, pretty close to 100%. They theorized that, and it was 100% theory, I would say, that the deep, dark reaches of the oceans maybe had a few creatures, but not life less. So when the Alvin got down to this ocean floor, they turned on their lights. They found an abundance of marine animals that were all feeding off very hot fluids being emitted from hydrothermal vents. They're kind of hot seafloor geysers. And much of that was sulfur ridden and phosphate, iron, many other types of things. Oddly, a lot of mercury and methyl mercury. I found that interesting. And so that's how they lived. That was the first thing that got me started. The next thing was, as a graduate student, I'd been studying continental drift or plate climatology. And that taught me that there's a lot going on with continents. So I put those two things together, and considering that most of the breaks in Earth's crust and segments happen in the oceans, I suddenly realized there was a lot more going on with oceans. And later on, ocean materials, I figured, went into the atmosphere. So light bulb went on, thought about the plate climatology theory, and since then I've been working on it. So, also, if you want to look at more details, you can go to the website.
And what is that website?
Plateclimatology.com. So to make sure we're all on the same page, let's talk about the premise. Increased tectonic activity, either locally or globally, equates to more faulting and volcanic activity, which leads to more heat and chemically charged heated fluid release from active geological features into oceans, subglacial polar areas, and atmosphere. This altered heat and fluid input has in past and still to this day affects climate and climate-related events. So really good premise, I think. Down below that are some of the things that geology affects. We're going to be looking at the upper four in some fashion. Okay. So if there's such a significant effect of geology on climate and climate-related events, why have they remained hidden? I mean, scientists have explored everything, right? They have all the data, they have all the answers. Well, that's not true. There are three reasons why geological forces have been hidden. The first one is remoteness. 71% of Earth is covered by oceans, which have an average depth of 14,000 feet. Difficult to get down there and measure things. The second reason is that another 11% of our planet is covered by glacial ice. In Antarctica, about 1.5 miles thick. Up in the Arctic, there's thick sea ice, and so it's tough to get down to these remote areas. So the second reason is lack of monitoring. It's difficult to monitor these remote areas. They have a buoy system. It's called the Argo buoy system across many of the oceans. Last time I checked, it was 3,881 buoys. They have restrictions though. They only go down to about 6,000 feet, and the average depth of the oceans is beyond that. There's also a limited number of them. So if you do the calculations, it's about one buoy for every 35,000 square miles. So that's not a lot. All right. Another thing about monitoring is that Gerlach in 1995 for the USGS took a look at the influence of geological forces, the amount that they emit, CO2 and temperature. Now, he only looked at 10 or so volcanoes, 5 in the ocean, 5 on land. That's a big problem. That was to establish, excuse me, the effect or magnitude of ocean emissions. Turns out there's somewhere around 1 million ocean features. So just looking at a few of those really doesn't give you a fair appreciation for the effect and the magnitude of emissions from the ocean. The last thing is atmospheric bias. I coined that phrase a little while ago, and it has to do with the fact that the largest data set on Earth is the atmosphere. A lot of data, it's very accurate, but as we all know, truth is not often because if you have a lot of data and accurate data. So scientists made conclusions and correlations actually to climate and climate-related effects, but I would contend that many of those are side effects, and we'll talk a little bit more about that. So there's some reasons why it's hidden. We're going to talk about Antarctica, the Arctic, El Nino, and ice ages. Let's start out with Antarctica. It's a pretty large continent, about the size of the lower 48 states. It's divided into two parts. West Antarctica, you can see there, is kind of the dark red, which is 25% of the continent's landmass, and then East Antarctica, which is the remaining 25% of the landmass. So what is this map? This is a surface temperature map. The surface temperature is measured about 3 feet above ground level. Ground level is ice, land, or ocean. This ground map, surface temperature map, only looked at the ice and the ground in Antarctica. And when it was released, it really was hotly debated. Why? Because it didn't show the preconceived notion that there would be uniform surface temperatures all across Antarctica as per, global warming. Instead, these very two distinct areas were just unusual. Since then, this map has been confirmed by numerous studies, NASA and British Antarctic Survey. So what causes this anomalous distribution of surface temperatures in Antarctica? This is the answer. It's called the West Antarctic Rift System. It covers about 1 million square miles, about 3,500 miles long, 800 miles wide. And we'll show you some proof that this entire thing is high heat flow. You'll notice as well that this perfectly matches the high surface temperature we saw on that preceding slide. So let's talk about a few areas that give us evidence that this is what's melting the ice and causing the surface temperature. We're going to start with Sandwich Island up to the north. That's where the fault is kind of conjoined. It's one single fault. We'll move down to Deception Island, 2 faults, bounding faults. Pine Island, Byrd we'll talk about together, and then Erebus. So let's start with the Sandwich Island area. This is a 3D bathymetric map on the left of the Sandwich Islands. You can see that there are numerous cone-shaped things on the bottom of the ocean, and then also cone-shaped islands. They extend up to where they're exposed. And several of those have erupted in the last few years. You can see there on that left image, a little thing that says erupting volcanoes. Now, if we look at the upper right slide, these are the three volcanoes that simultaneously erupted in September of 2016. On the lower slide, May 2016, is another one of these islands that erupted. It sent out huge amounts of ash and heat into the area. And according to environmentalists, it threatened the life of 1 million penguins. That didn't happen. They adjusted. So this area is very active. Now, we just, on the left slide there, we just looked at the sandwich area, which is kind of over to the right side of the slide where the fault is conjoined. Now we're going to move down to the left side of the slide. You can see the Antarctic Rift faults there's two of them. You can also see some indications of red circles. Those are volcanoes. We'll start with the large volcano that's kind of over there to the left where it says collapse volcano. The upper right slide is the Deception Island, which is a huge collapse volcano. And it's really an interesting thing because so you can see there's several other volcanoes on the remnants of the collapsed volcano. And those volcanoes have erupted 10 times between 1827 and 1995. The bay water in here is also very hot. Geothermal hot springs, you can see there on the left where it shows Fumarole Bay. The other area we're going to talk about in the Deception area is the Larsen Volcanic Plateau. If you look at the lower right of the slide, you can see where it says 16 volcanoes. That is the Larsen Volcanic Plateau. The lower right slide shows one of the volcanoes on the plateau. You can see that it's absent of ice. That's a direct indication that there's heat flow coming out of this. Also, early explorers that went across Antarctica saw fresh ash on the sea ice and the little bit of ice on land in this area. A follow-up study by the Chilean University very recently showed that there was also significant amounts of very fresh ash on this. So combine all this together, and it indicates that the Deception area is high heat flow and quite active. Now we switch down to that central area. Now the perspective here is a little bit different. You notice in the upper right-hand side, Antarctica is turned, so it's kind of a west and east. Of course, there is not a definite west-east in Antarctica, but you can see that the Marie-Byrd area is kind of tilted or laid flat. I'll call it west to east. So the dark red outline is the outline of the Marie-Byrd hotspot generated by a mantle plume. And for those of you who don't know what a mantle plume is, it is a thick column of viscous material about 18 miles down in the earth that flows upward in a big column and then spreads out in a mushroom shape once it hits the crust of the earth, the rock layers in the earth. This flow also has the potential to put a lot of pressure on the surface rocks. Sometimes it breaks through and it generates and fuels a lot of volcanoes. Now you look at the Marie-Byrd area and you see some circles. They're colored. Those are currently identified semi-active subglacial volcanoes. The red triangle there is also a currently active subglacial volcano. So this area has a lot of melt, and I think that that's not atmospheric warming. It's related to bedrock heat flow. Next, we'll go to the right side of the slide, and we're going to take a look at the Pine Island Glacier. This Pacific glacier is kind of the poster child for atmospheric warming for a long time. But you can see there's a hot spot, kind of the light red, on the left of there with lots of subglacial volcanoes. On the right side of the glacier, you can see that there's a couple hot spots and a lot of subglacial volcanoes there. Of note, in the last year, they've positively identified a subglacial erupting volcano beneath the Pine Island Glacier. So I would contend that the melting and quick release of a retreat of this glacier is not related to atmospheric warming or ocean warming. It's related to geological forces. Now, not shown in this, I'm going to go ahead and mention another glacier that is in that left hotspot area, left of the Pine Island Glacier. And there's another glacier there. It's called the Thortes Glacier. It's been in the press a lot because they've done some measurements and they found that there are huge caverns, vacant caverns, at the interface between the bedrock and the glacial ice. It looks like the glacial ice has been melted. That's again been attributed to some kind of complex interaction of the atmosphere warming the ocean and creeping up under this glacier and not a lot of the other ones in this area that are not have caves. So again, to me, this is a strong evidence that bedrock heat flow has a lot more to do in this area than was given credit. Now we move down to the southern end of the Western Arctic Rift, and on the left is a picture you probably have never seen before. It's not shown in the media presentations or by scientists that have worked it, unless you dig really deep into researches. This is Mount Erebus. It's currently erupting. It's a 12,448 foot high stratovolcano. You can see that some of the ice is melting on that. It's been erupting for many years mildly. And off to the distance there, you can see another stratovolcano. It's called Mount Terror, very large. So Antarctica in this end is pretty active, not inactive. It's not this flat plain of ice. To the right is a satellite view of Mount Erebus, Mount Terror, and Mount Byrd. It's kind of the upper part of your screen there. These volcanoes are adjacent to a large bay, Ocean Bay. And you can see a lot of big icebergs in there that are melting. Sea ice melts them. Well, what is happening here is that the volcanoes are warming the ocean and these icebergs are breaking away as a result of that, not atmospheric warming. On the right side of the slide, you can see there's a vertical dark line. It represents the east bounding fault of the entire Antarctic Rift. And then below that, you can see faintly what's called the Nansen Glacier, another poster child. When I looked at the Google Earth, I found that there were two very circular, cone-like looking features down there. And this, the fault and the volcanoes are probably a result of melting the ice in this poster child area. So that's Antarctica. All right, Arctic. We're going to start as we did in Antarctica with an overall geological view and the largest geological features. The hatched areas are ocean floor, high heat flow, rifts, and trenches. So for instance, the one on the right, you can see all the red triangle volcanoes. That's called the Mid-Arctic Rift. About 1,000 miles of that was researched by a Swedish university, and that 1,000 miles, they found hundreds, potentially thousands, because they couldn't cover the whole area accurately, of hydrothermal vents emitting huge amounts of heat. Also some seamounts, ocean floor volcanoes. So that's a very hot area. Over to the left, or west side, the Aleutian Island Trench. You notice that there's a lot of eruptions in the press in Alaska. Maybe you don't see many of the eruptions in the press in Russia, but there's about 90 active volcanoes up there at the north end of the trench, and there's usually 3 or 4 erupting at any time. The other thing we're going to take a look at is a mantle plume. We talked about that at Marie Byrd. If you look at Iceland there, there's a mantle plume there, and Iceland overlays it right now. Keep in mind that the mantle plume doesn't move. All right, let's go to the next slide. Big subject, Arctic sea ice melting. What you see here in white is the Arctic sea ice. I looked at the average for every November, so I'm going to talk about that, last 5 years of averages in November. And you can see with the white hatched lines, that's where the sea ice has been melting in November. So my contention is on the east side, the mid-Arctic ocean floor ridge, which is proven to emit heat, is what's melting that west side. On the east side, the Aleutian Island Trench heats up the Bering Sea, that little blob of blue, and that heat flow flows into the western side of the Antarctic Rift. There's been a lot of changes in animal patterns and heating in the Bering Sea, and this is what's melting that other side. Another really interesting thing about this map is that you'll notice that the sea ice is not melting against Russia or against Greenland or Canada. To me, that's more convincing evidence that the geological features are melting this. Now, I want to make sure that you understand that some of that connected land ice does melt, but the majority of the ice melts on the edges there, as I've demonstrated. Let's take a look at Greenland. We talked about Iceland. It's at the bottom there. That's where the mantle plume is. Now, referring to continental drift, Greenland actually used to exist southeast here. And as it moved northwest over the stable mantle plume, it heated the bedrock, and that heat has stayed there. It's called relic heat flow. And you can see that where the red area is and the tract of Greenland across the mantle plume. You can also see that there's some hot spots on the edges of Greenland, which are related again to heat flow. And that's where the majority of melting occurs in Greenland. Now, there's not as much melting noticed yet in the center of Greenland, but maybe Gregory, you could point this out at the north end of the track. Keep going. See that little blue right there, that little blue line that looks like it's pointed towards the Fram Strait, towards the that is a recently researched and definitely found 1,000-mile long subglacial river. And obviously, there's a lot of ice being melted in order to create a freshwater river of that size. The bottom is a slice into Greenland. It's another research study that confirmed that there was relic heat flow in red beneath the continent. You can see that heat flow, according to this article, extends up and melts the bottom of the sea ice, creating rivers. Over on the left side of that diagram, you can see that there's still faint indications of bedrock heat flow, and there it forms isolated lakes. They've been able to identify some large subglacial lakes. So I think we've showed where Antarctica has a lot of heat flow and is responsible for many things that are going on with the sea ice and glacial ice. At least we need to consider that, right? Okay. Next. All right, let's talk about El Ninos. Everybody knows about El Ninos. These are one of the largest climate affecting events, warming event of the ocean on Earth. They have the power to change the weather and climate trends. You possibly have heard that they create huge droughts. They do a lot of increased rainfall across this. And you see that red cone-shaped thing goes back on the left to a red dot. That red dot is the source point of all El Ninos in the history of time. And so that's kind of unusual. Why would they all occur at one point? Wouldn't there be other El Ninos and other points in the area? There's not. El Nino just occurs here, and that's the only source point. That kind of indicates that maybe there's something going on in the bottom of the ocean. I've investigated this, and it is. That area, that source point area, is one of the most active geological places on Earth. It is where Indonesia and New Guinea in that area and the Solomon Islands. There's about 5 major tectonic plates that converge here. It's part of the Pacific Ring of Fire, and it has a lot of active land volcanoes in it, and they found out there are other sea bottom active volcanoes. Another thing about El Ninos that shows that they're probably not the results of ocean current warming, but a point source, is that no other place on Earth do they occur, and the computer models put together to predict these have failed continuously for a long time. The upper right slide is a slice of a time video. Red is warmed ocean, the bottom of the ocean in black. You can see that that red area, which is over the source point, kind of has these needles pointing down. And these hotspots occur in bursts. And so this is a burst of energy. It gets carried by currents off to the right or the east to South America. The bottom slide there is an analog. That is a satellite view of a red source point, which is a non-moving Earth volcano. And as it sheds out hot ash, it forms this cone shape, just like El Nino. All right. Last thing about El Ninos, we talked about bursts. This is a picture of a time-lapse video that shows the development of El Ninos. El Ninos don't warm uniformly. They actually take time to build. And so on the left, you can see one of these areas that's warm in the surface of the ocean. These things are pulses of heat, and they move across the ocean to the east. They maintain their integrity. You can actually see one off there, the coast of South America. To me, pulses of energy like this are not related to continuous ocean currents or atmospheric warming of currents. These are blasts of energy from volcanoes. So that covers El Nino. All right, let's talk about ice ages. Everybody knows about them. In cold periods, there's maximum extent of ice age. This is covering North America here. The right slide shows the minimum extent. This has all been attributed in many cases to changes in the atmosphere, changes in the climate, and maybe that's correct. But in the next slide, we're going to take my look at and my interpretation of what might be the reason for changes in the so-called ice ages. Now, I want to tell you up front here that this is my hypothesis. I haven't seen it anywhere else. It's fine if somebody proves it wrong. I'm just putting it out there for scientific investigation. So this graph covers 450,000 years on the left, 450 on the bottom axis, 0 on the right. It also shows concentrations, atmospheric concentrations of CO2. A large concentration of CO2, the blue line is to the bottom, less CO2 to the top. It also shows atmospheric temperature, greater temperature in red. The line, the bottom is high temperature, atmospheric temperature, and then it goes up to a lower temperature on the top. So how do we know that this is a valid chart for 450,000 years? These parameters were taken from Vostok ice cores. Well, how can ice cores tell you about the atmosphere? Well, they've done this for a lot of years. They extract the ice cores from Antarctica, and it shows 500,000 to 1 million years. And they have methods that they can find some bubbles in the ice, or other methods that they can time when this ice was formed, and they can extract temperatures in those ice cores that relate to atmospheric and temperatures and CO2 concentration. The really big thing I want to emphasize here is towards the top there, you can see that the temperatures and CO2 concentrations level out. Well, you can see a couple of black lines there that show a normal level. I think this is the normal level of climate on Earth. It gets to that point and it's completely recovered. Then there are 5 really sharp spikes about 100,000 years apart. Those are related to Milankovitch cycles. Every 100,000 years, Earth changes its orbit around the sun. It also changes some of its other parameters, and that causes tremendous amounts of gravitational stress, primarily on the ocean faults, the big changes between continents, and it sends out huge pulses of heat that makes its way up into the atmosphere. When you warm an ocean, like a kettle of water on a stove, you heat it, it eventually lets bubbles out. That's what's happening here. You warm the ocean with these deep volcanic events, geological events. Heat, like I said, escapes into the atmosphere. CO2 goes into the atmosphere. These Milankovitch cycles and the volcanic pulses have been proven to be true, and massive amounts of volcanism by Lamont Doherty. So we'll see how that goes there. Last slide. All right. I guess this is a mantle convection cell, bigger than the mantle plumes. It's this big, huge yellow mass of viscous magma. I can refer to it as lava that comes up to the surface of the Earth. It breaks into the crust, and then that magma moves out to the sides and goes down back into the Earth. They're about 180 miles down to the Earth. So these are massive features. This is what breaks up the continents. This is what generates and fuels a lot of the geological features on Earth. So to me, I think this kind of wraps things up. Oh, one other thing. This is a 2-scale diagram. So the little thin ridge above the yellow convection cell is the crust of the Earth. If I was to put the oceans on here, they would be insignificant. So that gives you an idea of the perspective of these mantle convection cells. All right. What do you think?
I like it. Very interesting and very topical, particularly if we look at there was a recent Antarctic study that came out this week dealing with just what you're talking about, but they're blaming it on climate change, man-made global warming. And your explanation, particularly for it's fascinating, very interesting. I think we've all learned a little bit here today.
Thank you.
And I want to thank you. We've gone to the 30-minute limit, but
All right.
it's very, very informative, and I very much appreciate you sharing this with us. I will link your website on YouTube and Facebook to provide that to everybody. And I'll discuss with you offline if we can provide a PDF or PowerPoint of
Yeah.
your slides with the proper credit. I think a lot of people would be very interested in getting that.
Thank you, Gregory.
I appreciate, again, it's James Kamis, the father of plate climatology. You've now been dubbed, and I thank you so much. And again, tune in for our next episode of Climate Chronicles next week. Thank you very much.